Okay, good morning, everyone. Everyone take a seat. Very good. So, another morning of exciting reaction mechanisms in organic chemistry. If I can find some chalk here. Okay, we stopped last time talking or discussing the mechanism of the SN2 reaction. And one of the requirements we identified, and we discussed sterics and electronics for this, is that we postulated a transition state which goes through a pentacoordinated intermediate and which will then lead to the product. And we argued both on steric, but especially on stereoelectronic reasons, because the nucleophile would like to attack the sigma star orbital of the CX bond, that this attack should occur on a trajectory which would be 180 degrees, so the typical backside attack. The question is, how do we prove this? If you look at this reaction mechanism, one thing we touched at some occasions already, but did not really discuss too much, is that this transition state leads you to the result that this reaction should proceed with inversion of configuration. So if we would have a chiral center, this center should be inverted, and so you should get the opposite stereochemistry. But that does not really tell you if we have a 180 degree angle, right? It could be also, the same could be true if for some reason the nucleophile would come from here. So the fact that we have inversion of configuration and that the fact that this reaction proceeds in a stereoselective way distinguishes from the SN1 reaction, where we would have, again, let's look at the mechanism here. Where we would have a carbocation as an intermediate, and the nucleophile could attack it from either side, which should then lead either to this or to this compound. Now, this example I've chosen, since I have two hydrogens here, you would not be able to distinguish because both of these molecules are the same. But for example, if we would have a different substituent here on this position, this molecule would become chiral. And so in this case, these two, under the assumption that H would be R1 here, these would be enantiomers. And so you would be able, in this case, to by simply measuring or analyzing if you have a racemic mixture or if you have one enantiomer, you would be able to distinguish between the SN1 and SN2 mechanism. But as I say, you would not be really able to make that point, which we tried to make last time, that we should have a backside attack in a 180-degree angle. And there was something very instructive, and I would like to show you this experiment, how this was actually analyzed and attempted. And this is the so-called Eschen-Moser experiment. Conducted, to give you a feeling, not too long ago, longer ago than every one of you was born, but nevertheless relatively recent. And Professor Eschen-Moser did the analysis based on the assumption that if he would have somehow the nucleophile tethered into this molecule, into the molecule, then depending on the length of this spacer here, so depending on the length of the spacer, the nucleophile attack could occur in an intramolecular way. And undergo in this case a transition state which would look like this, as opposed to if this cannot reach around and form such a transition state, the alternative, so this would be intramolecular. And the alternative to this would be that the substitution takes place in an intermolecular way. And this would be simply that a second molecule so here we have our tether with the nucleophile, but of course the same thing can of course also occur in an intramolecular way, eliminating this. And then if you want to close the cycle here, you could argue that this would be the product. So in both cases, this is what I would like you to realize, in both cases the product would be the same. So you would have the nucleophile and the tether hanging off. However, once it would have been formed in an intramolecular way, and once it would have been formed in an intermolecular way. So this alone, if you don't do anything else, if you would just run such an experiment, it would still not help us, because we would get a substitution product, this substitution product in both cases, and it could have arisen by an intermolecular pathway or by an intramolecular pathway. And again, one would assume, and that was the rationale here, that if the spacer is too short, if this cannot approach in a 180-degree angle, then the intermolecular pathway should be favored. Now, how do we distinguish now between intermolecular and intramolecular pathway? And let me show you on the actual molecules this was done. And the technique which was used is a so-called crossover experiment. And what you do here is you introduce labels. So let me color the labels. You have a deuterated methyl group here in this substrate. And a nucleophile here, I filled this with live a little bit later, but let's just, in order that we are able to understand the experiment. And the other substrate that was used is the one which has a deuterated metal group. And let me be consistent here with my coloring on this position, and it has nucleophile here. And so if the reaction proceeds intramolecular, in those cases, intramolecular, so the idea here is that the nucleophile is attacking on the methyl group, and what you have here is an extremely good leaving group. This is a sulfonate ester, a tosyl group. We will go into leaving groups a little bit later, but already keep in mind that such sulfonate esters are excellent leaving groups which are used very often, not just in such an intramolecular context, to start or to activate substrates for nucleophilic substitutions. And so in this case, we would have as the product, we would expect here that this would be the product, and along the same way this would be the product. So in both cases, we obtain a product which has 3 deuterium labels. So it's not really 3D. So it's D3 products in this case. This would be the case if the reaction is exclusively intramolecular. If the reaction is intermolecular, things might change. And let me switch the boards. So I number these molecules 1 and 2 so that I don't have to write the structures again. And so in the intermolecular pathway, the compounds, two compounds of structure 1 could react with each other. In this way, you would get two D3 products, as we have discussed earlier here when we looked at the one intermolecular mechanism. If you react two of the other molecules, again, in the intermolecular pathway, you should get two D3 labeled products. But here, and this is the interesting case, if the molecule 1 reacts with the molecule 2, so the molecule 1 is the one which has the D3 group in the substrate, and then the molecule 2 is basically the nucleophile, where the nucleophile can pick up a CD3 group. And this should actually lead to 1d6 product, because this nucleophile here is picking up this CD3 group, so you have 6 deuteriums in your molecule. And the alternative is then that this nucleophile is picking up the methyl group above, and then this way you have one D0 product. And so the reaction, of course, always goes to completion. So in the end, we will have all the methyl groups which were on the sulfonate ester are being transferred onto the nucleophile, of course. And now you see something. This one here, so the D6 and the D0 products, you will only obtain if this is intermolecular. So this is unique for the intermolecular pathway. And in other words, if you have exclusively intermolecular, you would expect D0 to D3 to, okay, so it's D3 products from 1 and 1 and the D3 products from 2 and 2. So let me put a prime here. D3 prime to D6 would be 1 to 2 to 2 to 1. And if it is exclusively intramolecular, it would be D3 only. And so with this, it's very simple, because it is very easy to analyze this by mass spectrometry, where you simply are able very accurately to measure molecular masses by this technique. And so very easily you can distinguish between a D0, D3 product with this technique. And you have a lecture on spectroscopy in the moment, and I'm sure mass spectrometry will be covered in this way. Okay, so this was the setup. And so now let's look at some actual molecules where this was done. Okay, just need to be careful here. So this was one substrate. This was tested for, and then again, I'm not writing now all the labeled combination, but one CD3 molecule where the CD3 group was, one CD3 group was introduced here, and then the corresponding CD3 substrate was synthesized. And so if you would look at this, this is 1, 2, 3, 4, 5, 6, 7. This would go through a 7-membered intramolecular transition state. So 7-membered, 7 if it would be intramolecular. But the result was that this reaction exclusively is intermolecular. So clearly this is not sufficient. And you see this is interesting. If you would draw a transition state, it's very tempting. You see, I would need a 7-membered transition state where I would have the methyl group here, the sulfonyl group, the dimethylamino group, and now look how tempting, in this way, how misleading this is. Wouldn't it be tempting to say, oh, of course, looks good on the board, right? This cyclization should take place easily. And it's not, because you see for yourself here, if I draw this, it is not really a backside attack. So such a cyclization, and that is something you need to be aware of if you think about ring cyclization reactions of this type. In this situation, you will not be able to approach the molecule, what would be needed, on a 180-degree trajectory based on the nucleophile, based on the leaving group here. And so this is not possible intramolecular. Because the ring is simply too small. Now, very often you have different types of situations where you will have the leaving group not inside this ring. So here you needed the 180-degree trajectory. Sometimes the leaving group would be somehow like outside here. Where you have a situation like this. And so this would work because the trajectory now to come 180 degrees from the leaving group is very different than here, where the trajectory is would have to come from this side. So something like this might be okay. But the important thing is that you need to analyze carefully in such type of nucleophilic substitutions if you are able to do the SN2 type reaction. And we are geared to the idea that 6-membered and 5-membered ring transition states are very favorable. But in a case like this, even the 7-membered ring is not sufficient to provide the appropriate trajectory. And only, let me give you one last substrate here. only in this case, where we have now a 8-member transition state, if we attempt the nucleophilic substitution here, only here you saw some percentage of intramolecular, but still the majority, 84%, was intermolecular. So even in this case, even in this 8-membered ring case, so the tether is now one longer, the trajectory to reach around so that you approach with the nucleophile 180 degrees to the leaving group here. Wait a minute, I'm missing a substituent, a group here. We're missing one oxygen here. So we might actually even have a 9-member transition state here. Let me see this. 1, 2, 3, 4, 5, 6. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9 even. So even in this case, the majority, the major pathway was still intermolecular, although now apparently at this 9-membered ring, the 180-degree angle can at least is close now to be getting realized. But what that simply should show you is that this backside approach in an SN2 reaction is a very stringent requirement for these type of reactions. And I think it's again a very striking argument for this model that the attack really has to occur into this anti-binding orbital of the CX bond, which is simply aligned 180 degrees to the leaving group. Okay. So we looked at the substrates last time, at the reaction rates, or we discussed what is favorable for SN2 reactions or not. Reaction rates with respect to substrate. And the simple rule was primary alkyl halides always SN2, tertiary alkyl halides never SN2, and secondary it's possible. And here, at the same time, primary alkyl halides will never undergo SN1. Carbocation is not stable enough. Always SN1 on tertiary and secondary also. Both is possible. This is the one, these are the things you should simply memorize. I give you now some examples where actually the reaction rates were being measured, just to give you a feeling for this. These are numbers, of course, you should not memorize, obviously. So let's look at some reaction rates for SN2 reactions, and let's see if we are comfortable with what we see. So we look at some reactions where we are increasing the steric bulk on the on the center. So we go from methyl here to a primary, secondary, and tertiary halide. And so the relative rates were measured here against the nucleophile. If the relative rate of the primary alkyl halide is 1, you would expect that the corresponding methyl halide is faster or slower? Faster? Slower? Undecided? Hey guys, at least one undecided here. And again, 99.5% don't care, right? This don't care fraction has at least to move to undecided, okay? So, obviously, faster. And you see about 30 times. Slower. And basically not reactive. Okay, let's look at some more. We again take this one here as our benchmark example. Actually has this one here as our benchmark. And so both times we are looking now at a primary or every time we are looking at a primary reaction center so here the relative rate is set to 1 here. So all of these are primary, but what you see is that the center next to the primary center becomes progressively larger. In this case here, the one additional methyl group on the next to the reaction center does not make a big difference. But you can see that if you increase also the steric size 1 atom away from the reaction center by now adding progressively methyl groups here, the reaction rates go down to the point that to do a substitution on a primary carbon center next to a tertiary center, in this case we highlighted already in the last lecture, this is the so-called neopentyl position. It's very difficult. It's very slow in the SN2 reaction, but it's also basically very slow or impossible in an SN1 because the carbocation is not stable enough. And so to do nucleophilic substitutions on such substrates is next to impossible, but you can see already even a secondary center is slowing down reaction rates quite a bit. Okay, let's look at a different parameter. Let's look exclusively at secondary alkyl halides. And let's look how it is changing if you go from a acyclic to a cyclic substrate. And so if the relative rate on the cyclohexyl bromide is 1, would you expect that in an SN2 reaction, the isopropyl, the acyclic one, goes faster or slower? Faster? Slower? 2 for faster, 2 for slower, 96% don't care or are undecided. I don't know what we have to do here. Probably I have to bring gummy bears or so. Everyone who's raising their hand is getting a gummy bear or something like this. But it's very difficult to engage you guys here in this. So who said slower? 2 outed themselves for slower. You said slower or you said faster? I thought you said faster.
Yeah, for what?
For this one.
I think it's faster because
It's less sterically hindered. So the question is it less sterically hindered? Yes or no? Tough question. We have additional bulk here, of course. So yes, in a way, you would think it's sterically more hindered because some of these methyl groups are replaced. So you could expect some kind of an effect like here. Interestingly enough, it's a lot faster. And why is this? Yeah.
I guess it's because the cyclochromy can do the inversion quite easily.
Yeah. Again, do we still have the mechanism up? But again, keep in mind that in the transition state, where the nucleophile is approaching you have an inversion of that center. And if this is in a ring, then the whole ring has to flip. And that is relatively easy for a cyclohexyl moiety. And I think, as you have learned already in the second semester lecture, the inversion of a cyclohexane ring is quite easily possible. Does anyone remember the inversion barrier? Who thinks it's 20 kilocalories per mole? Yeah. Other ideas? You also 20? Okay. It's the right region. We talked about the idea bond strengths. Usually, if you talk about any type of carbon bonds, typically carbon-carbon, 100 kilocalories, carbon-hydrogen, same thing. Rotation around bonds in the range of 1 to 10. So with 20, you are too high. This is somewhere, I forgot if it is 10 or 12 or so, but it's somewhere around 10 kcal per mole. So it occurs very rapidly. But compare this to the rotation barrier you have in a butane molecule, which is roughly, I think, 3 kcal per mole. So flipping the ring takes a little bit more energy through the because you have to basically rearrange all the atoms around, but it's possible. But you see this reflected in the reaction rates here. Now, interestingly enough, 5-member ring is very fast, and that is due to that the 5-member ring is much more flexible. It has not such a defined chair type geometry. 5-membered ring has this type of envelope structure where more or less you have constantly movement of one of the CH2 groups, and apparently this trajectory you have to undergo here and then flip the 5-membered ring is much more easier because it does not have not that defined geometry like the 6-membered ring. And then if you go to the 4-membered ring, things go down in reaction rate quite rapidly. Now the ring strain here becomes severe. Let's look at the transition state again. Here in this type of arrangement, you would expect an angle between the R groups of about 120 degrees. It has to go through in the transition state if you have the trigonal pyramid. And so here you are at the angle of 90 degrees. Here you're still at 109. Here you are at the angle of 90 degrees. So you can clearly see that the strain for flipping the four-membered ring is increasing. And this comes then to the problem that three-membered ring halides basically do not react any longer because they cannot do the ring flip any longer. Okay? And as the last example, our last group of examples, let's look at if we substitute one methyl group through another chloride. So if you go from ethyl chloride to dichloromethane, so if the relative reaction rate is 1 here, what would you think will it be on the dichloromethane? Is it faster or slower? Who would like to argue that it's faster? Slower? At least some people are slower. Why do you think it's slower? Why do you think it's slower?
Because chlorine is very negative and it draws the electron density away from the carbon. So nucleophile attack should be higher or electron.
Very good. So the argument was it is electronegative. And so that's again a stereoelectronic. It's an electronic argument based on the idea that in the transition state of an SN2 reaction, you have an electron depleted carbon, and therefore any type of electron withdrawing substituent should disfavor that kind of transition state and should slow down the reaction. Anyone would like to name also steric arguments? You know the standard answer is there are steric and electronic arguments for everything. Anyone would like to argue on sterics here? In which direction that should go? Yeah?
Well, I think the methyl group, the first example is bigger than the chlorine.
Yeah.
Second example, I think it should rise up first.
Yeah, so the steric argument again would be methyl much, much bigger than chlorine. Always keep this in mind that methyl groups, any type which branches out with additional nucleus, is much bigger than chlorine. So even a bromine is much smaller than a methyl group in steric size. So sterically, clearly, the exchanging from methyl to chlorine clearly would on steric effects should favor the substitution here. And then rule of thumb very often is if sterics and electronics go against each other, and here we have the typical case again. The steric argument would say this should go faster. The electronic argument says this should go faster. Usually if sterics and electronics fight against each other, it's almost always that the electronic arguments win. And this is what we are seeing here. So the reaction rate goes down by a factor of more than 10 here. Okay, so this much about substrates. So let's talk about the role of nucleophiles in SN2 and SN1 reactions. Does the SN1, SN2, does the type of nucleophile influence the rate on an SN1 reaction? Yes? Why is this?
Because you have an intermediate and you can destabilize or stabilize it.
In an SN1 reaction, let's say this again. So it was said you have an intermediate. This is right. But let's look at the mechanism. We said in the SN1 reaction, dissociation takes place. And then in the second step, the nucleophile gets in.
Yeah, I wanted to say that the nucleophile is involved in the rate determining step.
Very good. Rate determining step again is the dissociation. This determines the rate of your SN1 reaction, nothing else. And so therefore, the role of the nucleophile is not there. I mean, it might be that it might not react at all for some reason. It's too big or whatever. But the rate is not determined by the nucleophile as long as this is true. If you constrict the nucleophile enough that this becomes the rate determining step here because it's very big or whatever, something you hardly ever see, then this might play a role. But in general, this is the rate determining step. You go through a high energy intermediate. You have to overcome this energy barrier to the carbocation and a much smaller energy barrier to combine the carbocation with the nucleophile. So basically here it has no effect on rates. And here, as you know, now we have a bimolecular reaction where the nucleophile is involved in a transition state, so it has a strong effect on rates. And the idea would be that a good nucleophile should accelerate an SN2 reaction, and bad nucleophiles should not. So the good nucleophile accelerates the SN2. Of course, we don't really know what a good nucleophile is. So what factors do you think make out a good nucleophile? There are 5. So the floor is wide open for suggestions. So far it's still very empty. What do you think makes a good or a bad nucleophile? What type of parameters will influence this? Okay, we have one. Size. Size matters, also in SN2 reaction. Okay. So let's put on size here. What else? Anyone else here? Yeah? The charge. What do you mean with the charge? I think it's a, maybe we can get this a little bit.
The more negative nucleophile is, the more valence electrons it has to
So you said the more electronegative it is, because we will see we will have two different type of arguments on charge. So the one thing you argue is electronegativity. The number of valence electrons.
Yes.
So your argument would be if you have more valence electrons, it's a better or a worse? Why is this? Because there are more possibilities to react. I'm not sure if I would argue on this type. Usually if I have I think it all goes in the right direction, of course. But if you have only few valence electrons, let's say sodium or magnesium, in order to reach the octet, it tries to take it away. It does not want to share the electrons, right? It wants to get rid of the valence electrons. If you have a lot of them, like nitrogen, so if you have magnesium, the easiest way to get to the closed shell is to get simply rid of the electrons rather than attacking somewhere and sharing it. If you have nitrogen, if this wants to reach an octet, it would either have to give 5 electrons away, or it would have somehow start sharing with start sharing. So indeed the way you phrase it is that more electrons, valence electrons, make a better nucleophile than less, is right. But I would not say it's because it has more possibilities. I think it's simply because it wants to, magnesium doesn't want to share the electrons. It just wants to get rid of it. And so I think the better argument here to phrase the same thing which you basically said is the term of electronegativity. The more electronegative or electronegativity should influence the strength of a nucleophile. But we need to argue just in a moment if a more electronegative or less electronegative element makes the better nucleophile. And then along this line goes the second argument, and this is how willing it is to share electrons. Right? And that is the argument of how easy it is to polarize. So polarizability is a second factor. And both goes on basically analyzing the valence electrons on the valence on analyzing the valence electrons on your nucleophile. Yeah?
Maybe the next argument is hybridization.
Sorry?
Hybridization.
The solvation. That's settled for solvation. Another argument is solvation. And this is the question if the nucleophile is easily solvated by solvents. You first have to break up that solvent shell in order that it can act as a nucleophile. And so along this argument that solvation tunes the strength of a nucleophile, of course along this line goes the question, goes the parameter solvent. So choosing the right solvent in nucleophilic substitutions becomes very important because this directly influences how good a nucleophile will be solvated or not. Okay, one is missing. If you think about the transition state, which should also influence this, is simply the strength of the new bond you're forming. Right? Because the strength of the new bond is already reflected in the transition state, and so if you have if nucleophile and whatever your substrate is, I choose a carbon substrate here, forms a very strong bond, then of course this also is influencing this. New nucleophile, whatever, X bond you're forming here. This last argument actually brings together nucleophile and substrate. And we will look at examples a little bit later in this lecture where it will become clear that depending on the substrate, a nucleophile might be good or might be not good, or might actually react at a different part of the molecule. Okay, so let's just go through some of these ideas. So solvation, we already briefly touched on that a nucleophile which is solvated by, and what kind of solvent molecules will solvate this well? Yeah? Polar ones, but what do you want? If you have a nucleophile, which usually, as we said, has free electron pairs, because this is what it needs to act as a nucleophile or to be even negatively charged, which type of polarity do you want? Polar solvents can be quite a bit. What is actually solvating the free electron pairs or even negative charges? Polarity alone is not enough, as we will see it in just a second. What is solvating? What part of the solvent is solvating a negative charge or a free electron pair? Yeah? The positive part. And what is positive part? Do we have positive parts in certain solvents? Hydrogens, right? Water, for example. So protic solvents. That would be the better term. So protic solvents solvate nucleophiles. And so a protic solvent, for example, the very easiest one is water. Hydrogen bonds, water, alcohols. Right? These are polar protic solvents. So in order to have a good nucleophile, which is not really solvated, you need to go to an unpolar solvent. What is the problem with unpolar solvents very often? If you think about nucleophiles, let's say potassium cyanide, something we will look in a moment for a different reason at. So protic solvents solvate nucleophiles. Unpolar solvents should not solvate the nucleophile, which would mean increased strength. But like many solvents, many nucleophiles are type of salts. So think about things like, for example, sodium cyanide, sodium iodide, so typically sodium bromide, so typically types of nucleophiles you like to use. Can you use unpolar solvents with these nucleophiles? Why is this? Why is it not a good idea to try a reaction in hexane with sodium cyanide? Because? Someone? Yeah.
It will absolutely dissolve at no way.
Yeah, it's not soluble. Right. So these are insoluble in unpolar solvents. And what is the way out? So what are very good solvents for nucleophilic substitutions if we need a strong nucleophile in an SN2 reaction? This might be different, as we will see in a moment, in an SN1 reaction. But what do we need? We need a polar solvent which is able to solubilize our nucleophile, but we don't want protons which will solvate our nucleophiles. We might want the other thing, we might want to have something which is able to solubilize our cations. And so the way out of here is that you have to use aprotic polar solvents. And there are quite a number. Does anyone know an aprotic polar solvent? Yeah? What? Acetone. Acetone is a relatively good one. And why does it work? It doesn't have protons, but it is able to, for example, coordinate the cations, like a sodium atom, and then make the sign. So it is able to solubilize the salt by coordinating to the cation, but leaving the anion alone. So acetone is a good one. Very good one is dimethyl sulfoxide, DMSO. And another one, very typically, which is also used a lot, is dimethyl formamide. Which is simply abbreviated as DMF. And these are very common and very good aprotic polar solvents. Okay, second thing, we already discussed the strengths of the new bond which is forming, simply because the bond strength is already reflected in the transition state. If you form a more stable bond, you will stabilize the transition state, and this way have a lower activation energy. So this is already reflected in the transition state. Size is important. What would be the argument here? Yeah?
The smaller the nucleophile is, the less it problems with other
Yeah, so you minimize steric effects the smaller the nucleophile is, right? Small nucleophiles are usually better than large nucleophiles for steric reasons. What actually happens if a nucleophile becomes bigger and bigger? How does it react then? What is the competition you have with every nucleophile? And that is also an important realization right now for distinction. What is the alternative for every nucleophile in a reaction? So again, we have a substrate. And so we want the nucleophile to do this. But what is the alternative? Sorry? Elimination. So the nucleophile acts as? Yeah, how do we call acceptors for protons? Base. Yeah. So the alternative is it can react as a base. And therefore start an elimination reaction which takes place on the carbon next to our leaving group. To do this. So we have either the reaction as a nucleophile, which would give us the substitution product. So this is substitution, but it can also react as a base. And this would then lead to the elimination product. And so therefore, again, and why, I guess, I think this is probably clear to everyone, but let's stop here. So basically, every nucleophile can act as a base, and also in the other way around. And now why does, if the nucleophile of the size of our nucleophile becomes bigger, why does it preferentially act as a base and not as a nucleophile any longer? Why is this? Yeah? The transition state becomes, in the substitution, becomes sterically more hindered, of course. And I think I would phrase it even simpler. The hydrogens are on the periphery of a molecule, on the outside, while here the carbon centers are more in the inside of the molecule, right? And so sterically, it is simply much easier to reach a proton than to reach a carbon center. On the other hand, the nucleophilic substitution usually leads to a more stable product because you form a stable new sigma bond, while here in your product you are forming a relatively weaker pi bond. And so thermodynamically, often the substitution is favored, but for steric reasons, the elimination is favored. And then you know at least what you have to do there. If you want to be sure that something is reacting as a base, you have to increase the steric size. So typically, if you have something like hydroxide, which of course everyone has the feeling that is the typical base, but hydroxide is both, it's a good base, but it's also a good nucleophile. And so in cases like this, you might always see competition. If then at least you want to push it onto the size to be sure that you have simply to be sure that you have a base, you increase the size, let's say to an alcohol derivative. This is the alcohol from the tertiary butanol, and then this way you only have a good base, but you do not have a nucleophile any longer. Now we have to think about the other thing. How are we able, even if we have sterically larger groups or small groups which have this competition between reacting as a base or reacting as a nucleophile, how can we distinguish between this? And we need to discuss this also in a moment. Okay, the fourth argument was electronegativity. So you think high electronegativity is good or lower electronegativity is good? And this will come a little bit, we will going now to discuss your argument on the number of electrons, and you will see that it doesn't hold really. Because on your argument you would say the most valence electrons might have a fluoride, followed by hydroxide, followed by amide, really. Right? So your argument would be, has the most electrons, would be the best nucleophile. The reason is exactly opposite, or the order is exactly opposite. So the nucleophilicity is going in this direction. And simply, why is this? How would you argue this? It's like in real life. Some people are very greedy and some atoms are very greedy, right? If you are a highly electronegative atom, you don't like to share. That's more or less the answer here. So strongly electronegative atoms hold the electrons very tightly to it. In addition, some of these strongly electronegative atoms like fluoride, it's very difficult to make fluoride which is not somehow solvated by protons. Solvation comes in addition. So although these are strongly electronegative, they are also solvate very well with Protic solvents. So we have also the solvation argument, which is often decreasing the strength of such a nucleophile. And then polarizability goes into a little bit in the same with the same idea. This is how easy atoms are willing to share their electrons, and that is also differs, and that differs especially not with the electronegativity so much, but it specifically differs also with size. So large atoms typically are easily polarized and are therefore better nucleophiles. And like in the combination, for example, of these two arguments, it makes sense so if you look at the nucleophilicity, it makes sense that, and let me say here right away, in solution, that strongly electron withdrawing groups atoms keep the electrons tied to it, so they are not so easily or willing to share this, so they are not so good nucleophiles. And then the same thing is true on the polarizability argument, that typically iodide is in the halogen row is the best nucleophile because it's most easiest polarized in comparison to bromine, chlorine, or fluoride. As you can see, and that makes it sometimes very difficult to argue these nucleophile strengths, this is what's seen experimentally, and it's seen in solution, where you see that in solution, the solvation of a large atom is also not as good as with a small atom, especially if you have protic solvents. So fluoride in water is extremely solvated and therefore not accessible at all for nucleophile attack, in addition to being electronegative, in addition to being not very polarizable. On the other hand, if you look at strengths of the new bond which is forming, which one is the strongest bond of, when we do is carbon fluoride, carbon chloride, carbon bromine, carbon iodide bond? What is the strongest bond which is being formed? It's the carbon fluoride bond, right? By far. It's by far stronger. And here we come again that the strength of the new bond, of course, takes place, but it can only take place if the nucleophile can even act as a nucleophile. But this makes it that in the gas phase, the order is actually reversed. And that the fluoride becomes the strongest nucleophile. And there, probably the argument on bond strengths, on forming an extremely stable bond, is taking over here, because in the gas phase, obviously, solvation doesn't play a role, and therefore the factor of forming a stable bond is most important here. So some of these five factors we have sometimes go against each other. The halogens are a good case where you can actually see reversed order depending on the reaction conditions you have. Now, in general, there are some other effects known which make a nucleophile better. And of course, the more electron-rich a nucleophile is, the better it should be. And there's something which is called the alpha effect. And this is that there are quite a number of nucleophiles which differ in the way that they have an additional heteroatom on the nucleophile attached. So this is a heteroatom effect. And what is being found, and you have this with quite a number of molecules, so also ammonia, compared to hydrogen. And these two are much stronger than these ones. So hydrogen peroxide is a much stronger nucleophile than water. Hydrogen is a much stronger nucleophile than ammonia. That's not so obvious. You cannot really draw resonance structures. Actually, based on the inductive effect, you could even think that it pulls out electrons. But it has been argued that simply because of the high electron density you have here through the lone pairs in these molecules, that these actually act like a donor, although there's no mesomeric effect. You cannot draw any type of resonance structures. Nevertheless, it's experimentally proven that such molecules are by far stronger than the corresponding molecules which do not have that second heteroatom. Okay, so this is a way, and the two ways you can argue this, again, you can say you can argue on the fact that you have repulsion actually here. And so once one of these electron pairs undergoes a nucleophilic substitution, the repulsion is being taken away. So how do we phrase this? So we have, in these molecules, we have lone pair repulsion. Which is not present any longer, or which is lessened in the nucleophile in the substitution product. And I think this is probably a pretty good argument to explain this, that simply in order to avoid this repulsion, one of the electron pairs readily engages in nucleophilic substitutions. Okay, it's almost over. And so without giving you this lecture, without giving you an explanation, I would just like to draw your attention that very often the substrate combination with a nucleophile could matter. And a very famous example is the nucleophile substitution with cyanide. And cyanide has an interesting structure. Cyanide has a lone pair on carbon, and it has also a lone pair on nitrogen. Yeah?
I guess the nitrogens only have one lone pair.
Which one? Here?
Yes.
Well, I just draw this as a p orbital. Right? It's just a p orbital. It's not a lone pair here. I meant that this is simply you're absolutely right, of course. It has only one lone pair. But I just wanted to depict the orbital here, if you would consider this being sp2 hybridized. Okay, so cyanide here has a lone pair on carbon. It has a lone pair on nitrogen. It could actually react with an alkyl halide in both ways. It could react to form what is called a nitrile, but it also could react on nitrogen to form an isonitrile. Some of the worst smelling compounds organic chemistry knows. If you ever work with isonitriles, everyone, not only in your lab, probably everyone on your floor will know. Okay? And interestingly enough, both of them can form, and it depends on our cyanide source. So potassium cyanide gives the reaction on carbon. Silver cyanide gives the reaction on nitrogen. And that's a different quality on the strength of of nucleophilicity, that the combination both with cations, but you will see more so with a substrate, can actually determine or can cross over which part of a molecule is the better nucleophile, right? You would conclude here in the first reaction, the carbon end is the better nucleophile. If you use silver cyanide, the nitrogen is the better one. And behind that is a very important principle, and that is what we are going to discuss on Friday. For now, this lecture is over, and we start the tutorial at 12 o'clock. Thank you.